Hello YouTube, and welcome back. We had a little technical difficulty on Friday. Something was glitching. So I'm re-recording. Here we go. Here's 903. What is x plus yi format? That's a plus bi form complex numbers. But I'm thinking of them with an x coordinate and a y coordinate so we can plot them as vectors on the complex plane. So you could also represent them polarwise with r and theta. What's this cis thing? That's what we're talking about. Okay, here we go. So here's our first question. Can you find r given that in your x plus yi form you have 1 square root of 3i? So 1 square root of 3i. We'll graph that in a little bit, but if you graph it in the first, it's in like the first quadrant of the complex plane. 1 is the real part, and square root of 3 is 1.732-ish, isn't it? Is the y part. So draw a vector from the pole or the origin to that point, and you have a vector representing the complex number. So what is the magnitude of the vector? So let's show the absolute value of 1 plus the square root of 3 times I. Be careful, capital I is reserved for the imaginary constant rad negative 1. Alrighty, and if we just run that, what did I do? Squirt. Oh, I spelled it wrong. Squared. And thanks, the absolute value of a vector is its magnitude, but what is that? How about we nify it? And note that's exactly the same thing as what we do in class: square it, add it, squared it, like the distance formula. So let's do it the other way. Show, you could do it this way instead, the square root of 1 squared plus the square root of 3 squared, which is just 3, but what the heck. And if we run that, we get 2. And if you want it to line up nice, you can nify it, I suppose, but it's just 2. 0.000000000. Okay. So yeah, so the absolute value function in Sage is the same thing as the magnitude of the vector. In this case, a complex vector, a vector representing a complex number in a complex plane, where you don't have an x-axis, you have a real axis, you don't have a y-axis, you have an imaginary axis. Okay. What if we want to go the other way around? What if you have r cis theta? You have r, the magnitude of the complex vector, and theta, the direction, going counterclockwise from the horizontal. Is r is 2 and theta is 60 degrees. So how do you convert that to x's and y's instead if you want? Well, we figured that out. It's r cosine theta. So that's what we're going to do. We're going to show the argument. Wait, where am I? Wait, I skipped something. Whoopsie. I didn't finish question 1. Whoa, back up. Question 1, I also want the theta, which is the argument of the direction. That's what I want for this x plus yi format number 1 square root of 3i. 1 rad 3i. Okay, so what do you do? Well, you could show the argument. Now, the argument is a Sage method that gives you the angle of the direction of a vector. And it's, what is it? 1 plus the square root of 3 times I. Don't forget capital I. All right, let's see what that does. And thanks a lot. So what if we numberify that? Now, if you do it this way, the arctan of rad 3 over 1, the arctan of rad 3 is 60 degrees or pi over 3 radians, right? Is that pi over 3 radians? It is. What if you wanted degrees? Well, take that value and multiply by 180 over pi, remember. Let's see if we get 60 degrees. If we want 60 degrees, 1.047 is in radians. That's fine. And, well, I have to numberify the whole thing. I just numberfied the 180 over pi. So put parentheses around everything that you're going to numberify. Or put it in the n method. But there you go. And you get 60 degrees, right? Now, what if we do it the way we usually do it? Show the arctan of rad 3 over 1, so squirt of 3. Okay, and run that. And thanks a lot. So let's numberify that so you get an idea what that is. I mean, that's what I inputted. Thanks. The output and input are the same. And again, it's in radians, so if you want to convert that. Oh, la la. How about, all right, how about times 180 over pi. Now, do we have to put the big parentheses around this again? And we do. So it's the same thing. So arctan of y over x is the argument of x plus yi. So we're good. And the absolute value of x plus yi is the magnitude, the squared, added, squared stuff we did in class. So either way, you get 2, and either way, you get 60 degrees. Okay, now, let's go backwards. What if you got 2 cis 60? There you go. So you have that vector, right? Can it convert back to x's and y's? And we figured out that x's are cosine theta, right? So let's do that. Show r, which is 2, times the cosine of theta, which is 60. I'm given 60 degrees, right? What does that mean? Well, be careful. Arctan, or inverse trig functions, give radian measure. And cosine and sine tangent and whatnot, they want to input in radian measure. So if I nify this, I'm not going to get the x, which was 1, because I didn't input radians, did I? Right, so I got to convert this to radians. So how do you convert degrees to radians? You multiply by pi over 180. And you should get back to x equals 1. There you go, perfect. And how do you get the y? Well, let's do the same thing. So, but it's r sine theta, right? So show 2 times the sine of 60 times pi over 180. And that's what we get now, and that should be the rad 3. And it is, and if you want to numberify it, you get 1.732-ish, right? If you like. Okay, there you go. Perfect. Nice. That's great. Okay. Now, so that's how you convert to r theta, or r cis theta format. That's how you convert to a plus bi form, or x plus yi form from r cis theta form. So r cis theta is just the polar form of a complex vector graphed on a complex plane. So let's plot some of this stuff. All right, now there's this crazy thing called list plot. So list plot is just going to plot a bunch of points, okay? What do I want to list plot? Let's list plot. Let's see. I'm going to make, well, a list. And in that list, I want to make a point. And in that point, I want a real part of, let's say, my number I, and the imaginary part of my number I. Alrighty. And what I'm going to do is I'm going to say, this is inside the list, right? Yes. For I in points. So points is going to be a list of its own. So points, let's see. Points, let's say points equals, it's a list of square brackets. How about, what do I want to put in there? Oh, 1 plus the square root of 3. How about that? So 1 plus the square root of 3 times I. Don't forget the capital I is reserved for square root of -1. And there you go. There's your graph. So you're going over 1 and up. Rad through is 1.73. Now this is not a square window, so the aspect ratio is messed up. Let's see. What if we throw in an aspect ratio? Let's see. Comma. Aspect ratio equal to 100%. So it looks better. There you go. So you're going over 1 in the real part, and rad 3, well, it's chopped off a little bit here. Rad 3 in the imaginary part. 1.732 something, right? Okay. All right, so like that, I could graph a whole bunch of stuff. What if I want to graph e to the I pi? What does that mean? E to the quantity I times pi. And remember, this was the polar format that we had on the calculator. Whoops, e to the. There you go. Where the number in front of the e, let's make it obvious, 1 times, is the magnitude of the vector, and pi is the direction, in other words, 180 degrees. So let's see what we got. What just happened? 1. Okay. And there you go. You get a vector from the origin, or the pole, if you're thinking of polar coordinates, which is 1 unit long, and the direction of 180 degrees of pi radians. There you go. Perfect. And if you think about it, this is a length of 2 and an angle of 60 degrees, or pi over 3 radians, right? Okay, nice. Alrighty. So there's that's r cis theta, that's r, and that's theta on the calculator. That's how the THETA does it, right? So what if I said, okay, let's do something crazy. How about comma 3 times 3 times what? What did I want? E to the quantity. What did I want? I times negative pi over 2. I times negative pi over 2. So we're going to go 90 degrees in the clockwise direction. So that's the equivalent of 270 degrees, or 3 pi over 2. And with a magnitude of 3. So run that. And there it is. So go 270 degrees of 3 pi over 2 radians and go a magnitude of 3 units, and there's your vector. Perfect. All right, so it's only graphing the endpoints. Just pretend. Use your imagination. Right? Draw a vector from the origin or the pole to the point. There's your vector. All right. So this is the real part, and this is the imaginary part. This is not the x-axis. This is not the y-axis. This is the complex plane. Okay. What else? All right, let's throw in another one. How about 4 minus 4i? No, how about negative? Let's see. We're in quadrant. We're not. Oh, let's go over here. 4 minus 4i. Yeah, something like that. All right, so let's do something down here. All right, so comma 4 minus 4 times capital I. Don't forget the capital I. And 4 over and 4 down. Perfect. Nice. I like it. Okay. Alrighty. That's nice. Let's see. Want to get fancy? Let's do this again. You know what, let's get even more fancy. What if I put in some labels? Can I put in some labels? Let's see. Just for fun, we've never done this. Just to show you can label your axes. Axes. How did I write this? Axes underscore labels is equal to a list. In that list, we could put quote real, comma, imaginary. And let's put imaginary in quotes also. Is that sufficient? So what I want is a label here for the real axis and a label here for the imaginary axis. Did I do that right? And don't forget the comma. How's that? Not defined. What did I do? Axes, label, equals. What the heck is that? Whoa, what did I do? Isn't that how I did? I've done this before. Axes, labels. Wait, that is right. Axes, labels. It was the equal sign was messed up. There you go. So this is the real part. There's the imaginary part. If you want to get a little more fancy, you could say of z. We usually say z equals 1 plus rad 3i or something like that, right? So of z. Can I do that? Let's see. There you go. That's fine. Leave it like that. That's fine. Okay, so now let's get a little fancy. What if we take this whole mess and do it again, but generate a whole bunch of points in a loop? So points is going to be, let's see, what do I want for points to be? E to the I theta, for theta in range from 0 to 2 pi, and count by pi over 12. Okay, that sounds good. Pi over 12 is what, every 15 degrees? So you should see a vector every 15 degrees. Magnitude 1, because it's 1 times e to the I theta, right? So let's make a list of points. 1 times, I don't have to say it, e to the quantity I times theta. Yeah, theta. Let's call it that. For theta in, how am I going to write this? In range from 0 to 2 pi, I'm going to go in increments of pi over 12. I don't know if I can use range for this. All right, let's see what happens. And no, you can't range. Right, it's not range. It's S range. If you want, yeah, a range, if you go from 0 to 10, you can do it integer-wise. I want S range, which is a bunch of floating point numbers, I think. There you go. So for 0, 15 degrees, or pi over 12 radians, 2 pi over 12 radians, 3 pi over 12 radians, right? So you get 1, 2, 3 pi over 12 radians is pi over 4, 45 degrees. 1, 2 pi over 12 radians is pi over 6, or 30 degrees, right? 1, 2, 3, 4 pi over 12 is pi over 3, or 60 degrees. Pi over 3 radians is 60 degrees. 1, 2, 3, 4, 5, 6 pi over 12 is pi over 2 radians, or 90 degrees. So you're going to get all the reference angles and even some more. And the quadrantal angles of 0 at 0 radians, pi over 2 radians, pi radians, 3 pi over 2 radians, and 2 pi radians. So there you go. So pretend you have a vector from the origin to each of these points that are all separated by pi over 12 radians and 15 degrees, just to show you a whole bunch of different vectors, complex vectors on the complex plane. There you go. Yay! All right. What else did we do? Well, we did some crazy powers. We said, okay, stuff like this. What if I said for I in range 1 to 4, remember range 4 gives you 0, 1, 2, 3, so 1 to 4 gives you 1, 2, 3, okay? What if I just show the expand of 1 plus the square root of 3 times I, capital I, to the little I. Look what happens. Oh, whoops, what happened there? Expand with an N, and you get powers of 1 plus square root of 3I, right? Okay, why did I get it to work with, okay, I want to expand it, right? Why isn't it expanding? Did I do something weird? I did something weird. What did I do? Oh, I didn't put it, okay. I opened the expand, I didn't open the binomial that I'm expanding, then I close the expand, then I close the show. There you go. So now I'm expanding. And these are powers of 1 plus rad 3 over 2, so to the 1, to the 2, to the 3. So the third power of 1 plus rad 3I is negative 8. We did that using R6 theta, we did that by FOIL, and we got negative 8. Okay, let's go backwards. What about, so now we can talk about roots using DeMoivre's theorem or R6 theta format. How about for I in range, let's do 1 to 4 again. Remember, range 4 is 0 to 3, so 1 to 4 is 1, 2, and 3, right? So now what are we doing? We're going to do roots. Let's see. So show the roots of negative 8. So how about quantity negative 8 to the 1 over I. So 1 over 1, 1 over 2, 1 over 3, the square root, the cube root, right? So there we go. 1 over I. And let's see what we get from that. And yeah, I'd rather see this in complex form. So how about we numberify that? Let's see. Let's take the whole thing and put it in a number format. So let's get a float out of this. And see what we get now. Whoopsie. I put the, what happened? Oh, I lost the close show. Close show. And there you go. So look at this. Negative 8 to the 1 over 1 is just negative 8 to the 1 is negative 8. Here's the square root of negative 8. Here's the cube root of negative 8. Don't we get back to where we started? 1 plus rad 3I, 1 plus rad 3I. So we got to figure out how to do DeMoivre's theorem backwards, and that's what we're doing next. All right, so have a nice day, YouTube. That was fun. Bye-bye. Hope that